Hello everyone, welcome back to this online class. Today we are going to look at Romberg integration, and in particular we are going to look at how to use trapezoidal rule to obtain the initial estimates and then improve our solution using Romberg integration. So we have this question. We are asked to evaluate the integral from 0 to 2 of 1 over 1 plus x with respect to x. Correct to 4 decimal places using trapezoidal rule with the 2, 3, 5, and 9 ordinates. Hence, use Romberg integration to obtain the most accurate solution. So let's see how to go about this kind of a problem. So when you look at our integral, the given integral, our a is 0, our b is 2, and our f of x is 1 over 1 plus x. So you can say a is equals to 0, b is equals to 2, our f of x is equals to 1 over 1 plus x. Remember, we are using trapezoidal rule to obtain the initial estimates. And remember the formula for the trapezoidal rule, just to recall the trapezoidal rule. That the integral from a to b of f of x dx is the same as approximately equal to h over 2 into f naught plus 2 into f1 plus f2 plus so many of them plus fn minus 1, then plus the last one, that is fn. The f naught all the way up to fn, those are ordinates. And what is important here is that when we talk of ordinates, there's a relation between ordinates and the number of subdivisions, that the ordinate is always equals to n plus 1, where n is the number of subdivisions. Now, let's start with the 2 ordinates. Then we go to 3 ordinates. Then we go to 5 ordinates. And then lastly, 9 ordinates. So you write here using 2 ordinates. So 2 ordinates simply means that in this case, our n is equals to 2 minus 1, because the number of subdivisions must be 1 less than the number of ordinates. So in this case, our n is 1. Having found n, we can now be able to compute the step size. H is equals to b minus a over n. So that is 2 minus 0 over 1. And so in this case, our h is 2. Remember, h here is the step size. So we need to come up with a table of x versus f of x. So I need here x and f of x. We are starting from 0. So remember, our f of x is 1 over 1 plus x. So when x is 0, what will be our f of x? Where there is x, you put 0. So that will be 1 over 1 plus 0, which is 1. Step size is 2. So from 0, add 2, you get to 2. When x is 2, what will be our f of 2? When you press it in your calculator, you need to get 0.3333. 3333, or simply 1 over 3. Now, therefore, let's call it t. In fact, here we could call it, instead of this integral, we could call it tn is equals to that integral. Or simply tn is this other side. is an approximation. So in this case, for the first case, we have n is equals to 1. So we'll now call it t subscript 1. T subscript 1 is equals to h over 2. Remember here we only have f0 and f1, only those two. So it is f0 plus f1, only the end ordinates. So when you substitute those values of h, f0 and f1, you need to get 1.3333. So this will give you 1.3333. That is correct to 4 dp. So that is the approximate value of that integral when you use one subdivision. Let's see, what about if we use 3 ordinates? What are we going to get as our approximate value of the integral? So you can write here using 3 ordinates. What does it mean? That n will now be equal to 3 minus 1, because the ordinates are 3, so n must be 1 less than the number of ordinates, which is 2. So once we have found our n, we can now compute the step size. H is equals to b minus a over n. That is 2 minus 0 over 2. And so in this case, our H is equals to 1. Now, having found H, we need to come up with a table of x and f of x. So I'll have here x versus f of x. Remember, we are starting from x is equals to 0, and the step size is now 1. So when x is 0, the result is 1 for f of 0. Add 1, that's the step size, so we go to 1. When x is 1, what will be our f of 1? That will be 0.5. And finally, when we add 1, we go to 2. That will give you 0.3333. So now our integral is now approximated by t2, because our n is 2. That is h over 2. Remember here now we have f0, f1, f2. So it will be f0 plus 2 f1 plus f2. If you use the formula, press this into your calculator. You know the values of f0, f1, f2, and you also know the value of h. In this case is 1. When you substitute and you press into your calculator, you need to get 1.1667 as your approximate solution. 1.1667. So this is when we use 2 subdivisions. Let's proceed. Now we need 5 ordinates. When we use 5 ordinates, what will you get? So you can write here using 5 ordinates. Automatically, we need to calculate n. So that will be 5 minus 1, which is 4. So that means we have 4 subdivisions. And so with that, you can now be able to calculate the step size. That is h is equals to b minus a over n. That is 2 minus 0 over 4. And so that is 2 over 4, which is 0.5. That's now our new step size. Let's come up with a table of x versus f of x. So right here x, f of x. So again, you prepare that table. We start from 0. When x is 0, our value is 1 for f of 0. Our step size is now 0.5, so we add 0.5, that will give us 0.5. F of 0.5 is 0.6667. 6667. Add 0.5, you go to 1. When it is 1, you get 0.5. Continue adding, you go to 1.5. And so the value there is 0.4. Continue adding, you go to 2. This will give us 0.3333. So now the approximation for this one is T4 when n is 4. That is h over 2 into, remember now here, this is f naught. So here we have f naught, f1, f2, f3, f4. So when you use the formula, it is f naught plus twice the sum of the middle ordinates, that's f1 plus f2 plus f3, and the last ordinate is f4. You know the values of those ordinates from your table. You can substitute into that formula, and now our h is 0.5. When you substitute and you press in your calculator, you need to get 1.1167. 1.1167. So that's our approximation when we use 4 subdivisions. And finally, when we now use 9 ordinates, 9 ordinates will mean that n is equals to 8. So you can write here using 9 ordinates. 9 ordinates. Let's calculate n. In this case, n is equals to 9 minus 1. And so that is 8 subdivisions. So you can now be able to find h. That's our step size. That is b minus a over n. That's 2 minus 0 over 8. 2 over 8 is 0.25. Our new step size. Come up with a table of x versus f of x. So that this table will now be very long. Something like that. We start from 0. The value here is 1. Our step size is 0.25. So we'll have 0.25. F of 0.25, that's 0.8. Continue adding 0.25, you get to 0.5. That is 0.6667. Next is 0.75. That will give us 0.5714. Proceed. When we add 0.25, we go to 1. That will give us 0.5. The next is 1.25. The corresponding f of x value is 0.4444. 4444. Continue adding, you get to 1.5. And so there's 0.4. Proceed to add 0.25. That will be 1.75. And now here we'll have 0.3636. And finally, we get to 2. That will give us 0.3333. So that is when we have 8 subdivisions. So now our formula is now T8. When n is 8, it is h over 2 into, remember now, here we have f naught, this is f1, this is f2, f3, f4, f5, f6, f7, f8. We go up to f8. So you'll have f naught plus twice the sum of the middle coordinates, that's f1 plus f2 plus f3 plus f4 plus f5 plus f6 plus f7. And then the last one is f8. you know the values of those ordinates, f0 all the way up to f8, you can substitute into this formula. And remember, h is 0.25. Substitute and press into your calculator. You need to get 1.1032. And remember, these values that we have found using trapezoidal rule. They are initial estimates. So I'm going to add a superscript 0 to mean initial estimates. So each of them you add superscript 0. Again here, they're just 4. Another one is here. And lastly, this one. So we have found initial estimates using the trapezoidal rule. Now we want to improve these approximations by using Romberg integration. So now you write here Romberg integration right now using Romberg integration. Remember the formula for Romberg integration that, let me write it here. This is the formula we are going to be using, the iterative formula for Romberg integration, that T2n at level m is given by 4m times T2n at level m-1 minus T subscript n at level m-1 and everything over 4m then minus 1. This is an iterative formula that is used in Romberg integration when the initial estimates are provided by the trapezoidal rule. Remember the subscripts that you see there, those are levels. So when m is 0, it means those are initial estimates. When m is 1, it's another level higher than those initial estimates. I'll tell you how to apply this formula in this kind of a table. So we need to come up with a table of this manner. So we'll have here n and then t sub n at level 0. A horizontal line and a vertical line. So what we do is to write the values of the subdivisions in the first column, that is on the left, and also the initial estimates that we found using the trapezoidal rule. So what we'll have here, when n is 1, what is T1 at level 0? We got 1.3333. That's what I write here, 333. The next was when n is 2. Our answer was T2 at level 0 was 1.1667. 1.1667. Another one was n is 4 subdivisions, and our value was 1.1167. And finally, when we have 8 subdivisions, we got 1.102, 1032. So there's 32. So that's what we have. Now, on the right-hand side of the vertical line, we will have here T to N at level 1. Now when M is 1, look at the formula. T to N at level M is given by the formula, this one. So in that iterative formula, you simply substitute M is equals to 1. So when m is equals to 1, what are we going to get? So let me use this bracket. So it means what I need to write here is 4 raised to 1 times Tn at level T2n. Remember, n is 1, so at level 0. So it is the value here. This is the T2n at level 0. When n is 1. So the value there is 1.1667. Then minus Tn at level 0, because m is 1. So these are the value. That is 1.3333 divided by 4 raised to 1 minus 1. So write your answer. That will give us 1.1112, 1.1112. Proceed again here. You'll have 4 raised to 1 times 1.1167 minus 1.1667 over 4 raised to 1, then minus 1. Again, write the answer here. That is 1.1, 1.1000. And finally, here we'll have 4 raised to 1 times 1.1032 minus 1.1167, everything over 4 raised to 1 minus 1. Again, the answer here should be equal to 1.0987. 0987. Go to the next column. Is now T2, 2n, I mean, at level 2. That means now our m is 2. The same iterative formula. So what we'll have here is now 4 raised to 2 times the value which we got as 1.1000 minus 1.1112, everything over 4 raised to 2 minus 1. So that's minus 1. Write your answer. That should be 1.0993. So we write here 1.0993. Similarly here, we'll have 4 squared times 1.0987 minus this other value, which is 1.1000, everything over 4 raised to 2 minus 1. And so the result here should give us 1.0986. 1.0986. We proceed to the third column on the right-hand side. So I'll extend this line. And then you write here T to N at now level 3. Now M is 3. Let's use the same iterative formula. We'll have now 4 raised to 3 times 1.0986 minus 1.0993, everything over 4 raised to 3 minus 1. When you press this in your calculator, you need to get 1.0986. So that's what we write here, 1.0986. So the last value that we have found here is very much important for us. it means this is the most accurate result of that approximation, that the integral from 0 to 2 of 1 over 1 plus x dx is approximately equal to 1.0986. So we can now conclude and write here that therefore, you say therefore, let me write it this side. Therefore, the integral from 0 to 2 of 1 over 1 plus x dx is approximately equal to, we have found 1.0986. That is correct to 4 decimal places. 4 decimal places. And so this is by using the Romberg integration. And if you look at the exact solution, you realize that the Romberg approximation is better than when we use the trapezoidal rule. It's better than all those values we got by using the trapezoidal rule. Let's see the exact solution so that you can take note of that. So write exact solution, exact solution, or exact value it is equals to, when integrated, it will be ln of 1 plus x from x is 0 to 2. Plug in the limits of integration, that is ln 3. When I put x2, we get ln 3, minus ln, when x is 0, we get ln 1. And you know ln 1 is 0, so the result here is the natural log of 3. You can press in your calculator, what is natural log of 3? In your calculator, let us see. In my calculator, ln 3 is approximately equal to 1.0986. Let me write it here. 1.0986 12289. 2289. So this is the exact value of that integral. When you round off to 4dp, you get 1.0986. And you see what we got using the Romberg integration? We also got 1.0986. So it tells you that Romberg integration will give the most accurate solution of a definite integral. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When you meet next time, we look at more problems involving Romberg integration. Bye-bye.